Hello people, welcome back. So today's topic is application of Laplace transforms in mathematics. Introduction. Laplace transform is an integral transform method which is particularly useful in solving linear ordinary differential equations. It finds very wide application in various areas of physics, electrical engineering, control engineering, optics, mathematics and signal processing. Application in physics. A very simple application of Laplace transform is the area of physics could be to find out harmonic vibration of a beam which is supported at its two ends. Let us consider a beam of length L and uniform cross-section parallel to the yz so that the normal deflection W of x, t is measured downward if the axis of the beam is towards x-axis. The basic equation defining the phenomena is given below, which is Wn is equals to pi square into n square divided by L square into root of EL divided by m. Here n is equals to 1, it represents the fundamental vibration, and n is equals to 2 represents the first harmonic, and so on. Application in electric circuit theory. The Laplace transform can be applied to solve the switching transistor phenomena in the series of parallel RL, RC or RLC circuits. A simple example of showing this application follows. Let us consider a series RLC circuit as shown in the figure, to which DC voltage V0 is supplied. Now we apply Kirchhoff voltage law to the circuit. Application in power system load frequency control. Power systems are comprised of generation, transmission and distribution system. A generating system consists of a turbo generator set in which a turbine drives the electrical generator and the generator serves the loads through transmission and distribution lines. It is required that the system voltage and frequency has to be maintained at some pre-specified standards. Frequency have to be maintained at 50 or 60 Hz and voltage magnitude should be at 0.95 to 1.05 per U. In an interconnected power system, load frequency control and automatic voltage regulator equipment are installed for each generator. The controllers are set for a particular operating conditions and take care of small changes in load demand to maintain the frequency and voltage within specified limits. Changes in real power is dependent on the rotor angle, and thus system frequency and reactive power is dependent on voltage magnitude, that is, the generation excitation. In order to design the control system, the initial step is modeling of generator, load, prime mover, and generator model. The modeling of generator by applying the swing equation for synchronized machines. Model. The loads in the power system comprise of different kinds of electrical devices. Some loads are frequency dependent, such as motor loads, and other loads like lighting and heating loads are independent of frequency. Sensitivity of the loads depend on the speed load characteristics of all drivers. The speed load characteristic of composite load is approximated by delta P is equals to delta PL plus d delta W, where delta PL is the non-frequency sensitive load change and d delta W is the frequency sensitive load change. D is expressed as the percentage change in load divided by percentage change in frequency. So here's the block diagram for generator and load. Mover model. Prime mover is the source of mechanical power, which can be hydraulic turbines or steam turbines. The modeling of turbine is related to the change in mechanical power output delta Pm to the change in steam valve position delta Pv. The simplest prime mover model for a steam turbine can be developed by a single time constant Tt, and hence the resulting transform function is as follows. Gt is equals to delta Pm divided by delta Pv. So here's the block diagram for prime mover.